In this video, we will see the basic introduction of organic chemistry. We will see what is organic chemistry and why is it important. Organic chemistry is the branch of chemistry which deals with the study of carbon compounds and mainly its structure, properties, composition, reaction, and preparation. And earlier it is believed that organic compounds are obtained only from living things, so the name organic. Some examples are carbohydrates, lipids, and protein. And then scientists were able to synthesize the organic compound named urea in the laboratory. After synthesizing urea in the laboratory, several other organic molecules were synthesized. Here is another example, which is very familiar organic compound named aspirin. There are 9 carbon atoms, as you can see from the structure, and the red dots represent oxygen atom, and there are 4 oxygen atoms, and the rest are hydrogen atoms. So these are hydrogen atoms, and these are oxygen atoms, and these are the carbon atoms. So we can see the formula is C9H8O4. Aspirin is a medicine, and like aspirin, there are several other organic compounds plays very important role in medicine. Not only in medicine, it plays an important role in our daily life because food, clothes, paper, ink, rubber, soap, perfumes, etc. are important for us for proper living, right? And organic compounds are important constituent of many products, and the common element present in all these molecules is carbon. Carbon belongs in the 14th group in the periodic table. So in organic chemistry, we are studying the compounds formed by this carbon. Here is a flow chart for the classification of compounds. Okay, so we are classifying under functional group based on the functional group, the functions of each group, how is that behaving. Okay, so we have main 3 categories. That means we are dividing the compound formed between carbon and hydrogen. So if it's only carbon and hydrogen in the compound, we call it as hydrocarbon. Hydro means hydrogen, carbon is C, right? So hydrocarbons. And the bond formed, the compounds that is formed between carbon and Z. Z can be any other element. Okay, so only single bonds we are talking about. So that is sigma bond, right? Okay, and then another classification is the carbon forms a compound with oxygen. Okay, so that is carbonyl group compounds we will learn. So under compounds formed between carbon and hydrogen. So under hydrocarbons, we will learn 3 classification. No, actually mainly 2 classification first, and that is aliphatic, that is fat forming, and then aromatic, that means smell, aroma, you know that, right? It gives some certain order forming compounds. And under aliphatic, we are learning 3 classification again, that is carbon to carbon single bond, carbon to carbon double bond, and carbon to carbon triple bond. Okay, so this is triple bond. Okay, so these are the classification in general. So let us go ahead and visit each one in detail. First, I will go to the aromatic one. Okay, so the typical or the simple aromatic compound in organic chemistry we are dealing with is benzene. So that is nothing but carbon bonded with in a cyclic form with a alternate double bond. That is benzene with the formula C6H6. So ball and stick model, you can see that each black ball here is carbon and each white one is hydrogen with alternate double bond here. And if this benzene is attached to any other organic compound, we will call this benzene group as phenyl group because it is using that hydrogen to bond with another compound here. So we will not have C6H6 in the formula now. It will be only C6H5. Okay, since it is cyclohexane, we have 6 of them: 1, 2, 3, 4, 5, 6. So cyclic compound, so cyclohexane, and it is called phenyl cyclohexane. That is the aromatic compound. So, but we are going to discuss this one later, but we are going to concentrate on the other classification I have shown you in the previous slide. So under hydrocarbons, we have seen aliphatic, right? Hydrocarbons, aliphatic and then aromatic. So aromatic I said, and now this is the aliphatic one. So under aliphatic one, that is, we have three, that is carbon to carbon single bond. So carbon to carbon single bond. So this R can be any number of carbon atom. It's not only one. We can have plenty of carbon atoms here. That is generally represented by the letter R, and the simple example is CH3C to C. Only one carbon atom here with a 3 hydrogen, correct? So that is called alkane. You look at that difference in the spelling with the next one, which is alkene with a double bond. Okay, so that is the example here. 2 carbon atom connected with a double bond and 2 hydrogen on each carbon. And the third one is called alkyne, which is YNE when there is triple bond, and the C to C triple bond here. So we already discussed about the aromatic one, and we have to go a little more in depth in each aliphatic one: alkane, alkene, and alkyne. So how do we know when we see a compound, which one is it alkane or alkene or alkyne? So we can use this general formula to identify that one. So for example, that N gives you a number of carbon atom. Okay. So if you have 5 carbon atoms, what we will do is we will multiply that 5 with the 2. So 5 times 2 is 10. 10 plus 2 is 12. So if it is written like this, even without drawing the Lewis dot structure, we can say that is alkane, ANE ending, which is going to be saturated. Saturated means there is no double bond or triple bond. We will have all single bonded with a carbon to carbon as well as carbon to hydrogen. Okay, so this way we can see that. So if it is 5, we will just show 5 carbon atoms, and we will show everywhere single bond with a hydrogen. Okay, so everywhere we can write hydrogen. So we can say that there are 5 carbon bonded to 12 hydrogen, which is an alkane, which is saturated, means we don't have any double or triple bond. We call it as saturated. And how do we know for alkene? Alkene, we will have a formula CnH2n. We are not adding plus 2 here. So what will be the formula if there are 5 carbon atoms? It will be C5H10 only. So in this case, what's the formula going to be in this structure? There are 2 carbon atoms and there will be 4 hydrogen. Okay, so if it is 5, how are we going to write? 1, 2, 3, and 4, and 5, correct? And we have to have 10 hydrogen. So what I will do, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It not necessarily you have to put on the second carbon here, a double bond you can put anywhere, but wherever you are putting on that particular carbon, you will have only 2 bonds with 2 other elements connected. So for in this case, if it is carbon 2 and carbon 3, and if I'm numbering it as 1, 2, 3, 4, and 5, I will see that one is in between second carbon and third carbon. There is a double bond. So the second carbon is connected to another carbon and another hydrogen. Third carbon is connected to another carbon, and hydrogen, like that. Okay, so but the fourth carbon is connected to 2 hydrogen and 2 carbon. So it doesn't matter where you're putting the double bond if it is not given specifically which carbon atom the double bond is. Okay, so that's how the formula works. And for the alkyne, the formula will be CnH2n minus 2. So if it is for 5 carbon atoms, I should have 10 minus 2, that is 8. So in this case, we can draw that one in a minute. In this case, what's the formula? Let us see. C2H2, right? Okay, so let us draw for C5H8. First, I will do 1, 2, 3, 4, and 5. So since it didn't mention where to put a triple bond, I will just put the triple bond here in the beginning, and I will see how many hydrogen. 1, 2, 3, 4 bonds around each carbon. 1, 2, 3, 4 already here. So for the second carbon, already 4 bonds are there. So I don't have to have a hydrogen on that carbon. And I'm going to put hydrogen here and hydrogen here in order to make 4 bonds around each carbon. So I will put like this. And I can count and see whether the hydrogen is matching with our formula. So I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen. Okay, and 1, 2, 3, 4, 5 carbon. So I have 5 carbon. So that's how we can actually identify whether the given compound is alkane, alkene, or alkyne using the formula. It's easy to remember. So first one starts with CnH2n plus 2, more hydrogen in this case of alkane, and then CnH2n, and then I will subtract the number of hydrogen atoms are decreasing. You can see that. Okay, so when the number of hydrogen atoms are decreasing, I can see a double bond and triple bond is forming. We call it as unsaturated. Means we can add more to that one. Okay, the other one is saturated and this is unsaturated hydrocarbon. All right, so the formula, remember, so that it is easy for us to identify whether it is an alkane, alkene, or alkyne. Since alkanes are unreactive and it forms carbon to carbon single bond, alkanes are very, very unreactive. It does not have any reactive sites. So we have unreactive alkanes because all bonds are saturated. It does not have any reactive site. It does not have any functional group in it. Functional groups are reactive sites. So this forms a very long polymer by combining itself unlimited number. So poly means many, and it's going to be staying on in the land for many years, several years without degrading. So because of its unreactive nature. All carbon atoms in alkanes look similar and it is hard to recognize which is which, right? So chemists came up with an idea of classification of these carbon atoms depends on the number of carbon atom directly bonded to one of them. Say for example, if a carbon atom is attached to one other carbon atom like this in this case, we call that one as primary carbon atom. If the carbon atom is attached to two other carbon atom, we call it as secondary carbon atom. Similar to that, if a carbon atom is attached to three other carbon atom, we call it as tertiary carbon atom. And the last one, carbon can have only 4 bonds around it, right? So if the carbon atom is attached to 4 other carbon atom, we call it as quaternary carbon atom. So if we know the carbon atoms like primary, secondary, tertiary, and quaternary, we can classify hydrogen also same way. If the hydrogen is attached to a primary carbon, we call it as primary hydrogen. And if it is attached to a secondary carbon, we call it as secondary hydrogen. And if it is attached to a tertiary carbon, we call it as tertiary hydrogen. We cannot have quaternary hydrogen because all bonds are satisfied with the carbon. So we cannot attach any more atom to that carbon, right? Sorry. So now when you see this type of structure, how can we recognize the primary, secondary, and tertiary? Let us say that each end and bend are carbon atoms, right? So and then what we will do is we will draw the bonds around each one. So then we have only one bond for the first carbon here. So one bond, that means it is attached to only one other carbon atom. So that means this is going to be a primary carbon atom. And the second carbon numbered here is attached to two other carbon atom on the left side and the right side. So we call it as secondary carbon atom. And the carbon atom number 3 attached to two other carbon atoms left and right. So we have another primary carbon atom here. Sorry, secondary carbon atom here. And the carbon atom numbered 4 is attached to three other carbon atom. We classify that one as tertiary carbon. And the carbon atom on the top here, I can number it as 5, which is attached to only one other carbon atom. So we call it as, again, primary carbon atom. And this carbon atom is attached to two other carbon atom, one on the left, one on the right. So we call it as secondary carbon atom. And the carbon atom, this one I'm going to number it as 6. And this one I'm going to number it as 7. So the number 7 is attached to four other carbon atoms. So we call it as quaternary carbon atom. And then I'm going to number this one as 8. This is connected to only one other carbon atom on the left. So we can call it as primary. And the number, I'm going to number this carbon as 9. So that is attached to only one other carbon atom. So again, this is primary. And the number 10 is attached to only one other carbon atom at the bottom here, which is 7. So we can classify that one is also as primary. That's the way you are going to classify primary, secondary, quaternary. And the hydrogen attached to that one, we can call respectively primary, secondary, tertiary, like that, right? Okay, so if we are taking another example, 1, 2, 3, 4, and I can draw with a branch here, with a branch here, say for example. And also we can put branches here. So that means each bend and end are carbon atoms. I'm going to pick another color. So here, 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 this is carbon, this is carbon, this is carbon. And then we will just look at which one is attached to which one. So this carbon atom number 1 is attached to only one other carbon atom, so primary. This carbon atom number 2 is attached to two other carbon atoms, so it is secondary. The carbon atom number 3 is attached to three other carbon atoms, 1, 2, and 3. So it is tertiary. And number 4 is attached to two others, so it is secondary. And number 5 is attached to 1, 2, so secondary. And the carbon atom number 6 is attached to 1, 2, 3, and 4 carbon atoms, so we can call it as quaternary. Okay, so that's how we can classify carbon atoms into primary, secondary, and tertiary. So the hydrogen atom attached to that one, we can classify accordingly. And now we have to look at how can we name each individual hydrocarbons, whether it is having a single bond, double bond, or triple bond. So for that one, we have to go with International Union of Pure and Applied Chemistry. What is that? Is in short, we say that is IUPAC, International Union of Pure and Applied Chemistry. So that's a method we have to follow. There are certain rules by IUPAC, so we have to follow those rules. So first rule is we have to use the prefix given by IUPAC. For if there is only one carbon, we have to use a prefix meth. If there are two carbon atoms, we have to use the prefix eth. 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, 10 dec. Exactly the same way we were doing for naming covalent compounds. I hope you remember we learned in the first year chemistry, if it is 1 mono, 2 di, 3 tri, like that, 4 tetra, remember? And now we have to remember these prefixes to name the organic compounds, not the covalent. We are not using this one, okay? Even though some of them matches here from pent onwards, it is matching, but the first 4 is different. So let us see, give the prefixes for the following. C2, C2 means what? 2 carbon atoms, eth. So we will have the prefix eth. And for carbon atom, we will have the prefix but. And 5, we will have the prefix pent. From the table, you can see 7 is hept, and 8 is oct, and 10 is dec. Okay, so this is how we have to start with to name the organic compounds. And now let us see how to name it complete. Depends on whether it is alkane, alkene, or alkyne. So to do that, we should know whether it is a long chain carbon or branched chain carbon. I'm going to talk about only the straight long chain carbon in this chapter, in this module. So we will learn in detail for the branched and other functional groups later on whenever those respective chapters coming. So now we will just learn the basic, the fundamentals of that one only. Okay. So first we have to see how many carbon atoms are in the longest continuous chain and find the prefix for that one. And if it is an alkane, we just have to add ane towards the end. That simple it is. Okay. So just count it. So for example, the simplest one, let us see this one. We have how many carbon atoms here? 2 carbon atoms. So if there are 2 carbon atoms, I have to start with the prefix. So the 2 carbon atom, the prefix is eth, right? And now how do I know it is alkane? Because I know there are no double or triple bond here. This is saturated. So that is an alkane. So I have to end the name with ane. So I will end the name with ane. So ethane. Okay, so another, let us say C, and all are bonded with a hydrogen. So we don't have a long chain here. We just have one carbon. So we have to use the prefix meth. And since it is saturated, no double or triple bond, I have to end the name in ane. So this is methane. This is what you always heard, methane, methane, right? The methane gas. All right, so then if I have 3 carbon, so 1, 2, and 3. So we will have all hydrogen attached to it. So I don't have any double bonds. So I have 3 carbon atoms. So I have to use prop as a prefix. Since it is saturated, I have to add ane to the end of the name. So propane gas. You are familiar with all these gases, propane and methane for sure, right? Okay, so let us see some more examples. Okay, here you can see we just discussed CH4. So I will just show you here the name. I will just write that name, methane, and the structural formula can be Lewis dot structure. So I have CH4 like this. Okay, so either you can write the structural formula or condensed formula or molecular formula. For this one, it is same CH4. We don't have any other molecular formula or condensed structural formula. Or you can write skeletal formula. For CH4, it is same. So we don't have to worry about it. But for the second one, you can see C2 means eth is the prefix, and C2H6, is it alkane, alkane, or alkyne? So CnH2n plus 2, is it agreeing? Let us see. N equal 2 here, so 2 times 2 is 4, 4 plus 2 is 6. So it is an alkane. So I have to end the name in ane. And we can draw the Lewis dot, putting all hydrogen here. If you are drawing the skeletal form, we will just draw like that, right? And if you want to write the condensed form, you can write CH3, CH3. If you want to draw the Lewis dot, we will do just like this, Lewis dot, right? Okay, so that's how it is. And now C3H8, is it alkane, alkene, or alkyne? So I will just use the formula. 3 times 2 is 6. 6 plus 2 is 8. So this is again alkane. So I have prop is the prefix and ane as the end. And Lewis dot will be 3 carbon atoms and the rest of it hydrogen. And if you want to draw the skeletal formula, 1 carbon here, 2 carbon here, and 3 carbon here. Okay. And then C4. So C4 will be, okay, C4 will be but as the prefix, ane as the end, butane. So we have to have 4 carbon and each carbon atom is attached to hydrogen because it is saturated. So for the skeletal formula, 1, 2, 3, 4 carbon atoms. Condensed formula, CH3, and I have 2 CH2 groups in between, and I can write CH3. And now see 5H12. So 5 times 2 is 10 plus 2, 12. So that is again an alkane. So the name should end in ane. And 5 carbon atom means pent. So I will write pent, ane, pentane. So how can I draw 5 carbon atoms? 3, 4, and 5. And connect, 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 connect with the hydrogen. So 1, 2. Let me erase my, okay. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. So CH3, and I have how many CH2 in between? 3 of them, and CH3. Okay, that's how we can write and name the saturated hydrocarbon, which are alkanes. If it is an alkene with a double bond like this, no big difference. Only difference is you will end the name with a ene and you will number the carbon atom in such a way that the double bonded carbon will have the least number. What does that means? Let us see. So the name should end in ene because I already see a double bond here. And now I have to number the carbon atoms in such a way that the double bonded carbon here should have the least number. So 1, 2, 3, 4, and 5. If we are numbering from right to left, it will look like 1, 2, 3, 4, and 5. Look at the numbers here. So 2 is the least, not 4. So I will go with this from left to right in the numbering. So how can I name it is the same method. So there are 5 carbons, so I have to start with the prefix pent and the double bond present, so the name should end in ene, pentene. Okay, so that's the only difference for the double bonded carbon. If it is triple bonded alkyne, let us see how to do that. The same usual method, only difference is what? It's going to be YNE ending because it is an alkyne. I can see a triple bond and the number should be the least number for the triple bonded carbon. So it should go like this. So there are 5 carbon. So I have to have the prefix pent and it should end in YNE, pentyne. That's the only difference for triple bonded carbon atoms. To see these examples, how to name them and how to identify whether it is an alkane, alkene, or alkyne. C2H4. C2H4 means 2 times 2 is 4 and I'm not adding or subtracting, so that is an alkene. So the name should end in ene. There are 2 carbon atoms, so the prefix is eth and the name should end in ethane. So how can I draw this Lewis dot is carbon to carbon double bond and satisfy the other bond by hydrogen. So you can see that C2H4, right? So that means CH2, CH2, all right? And C3H6, 3 times 2 is 6. So that again ene ending because that's an alkene. So that is prop is the prefix, and so the ending or suffix is ene, propene. So that means I have 3 carbon atom. It did not mention on which carbon, so I'm going to put it here. So 1, 2, 3, 4, 5, 6 hydrogen. So CH3, CH, CH2. Okay, so then now say 4H8, 4 times 2 is 8. So that will be again alkene. So but prefix and suffix is ene, butene. So 1, 2, 3, and 4. So I'm going to put one double bond here. How do we know only one double bond or two double bond, right? So here C4H8. So the number is actually just for one double bond because 4 times 2 is 8. So now let us see by putting one double bond, how many hydrogen here now? 2 and one hydrogen here. So 1, 2, 3, 4 bonds around that carbon. So 2 plus 1, 3 hydrogen, 4 hydrogen, 5 hydrogen, 6, 7, and 8. So only one double bond. So you can see that one by drawing the Lewis dot as well as by looking at the formula. So this is our butene. And now if there are 5, pent is the prefix, and 5 times 2 is 10, so that ending should be ene. Why is it coming like that? I have no idea. Okay, so that is pentene. Okay, so C. First I will draw that, and I will put a double bond anywhere you want, and then 1, 2, 3, 4, and then here 3 already, so one more, 3 already, one more, 2 only, so one up and down, and you can see that we have 3, 4, 5, 6, 7, 8, 9, 10 hydrogen. Okay, so that's how we are going writing the name and the formula. Now let us do these examples. So we can see C2H2. C2H2 is, so with the formula we can try 2 times 2 is 4, so it is not ene, and 4 minus 2 is 2, so it agrees with the formula CnH2n minus 2, so it is alkyne, so the suffix is supposed to be YNE. So there are 2 carbon atoms, so 2 carbon atom means the prefix is supposed to be eth, so eth, and the suffix is supposed to be ene. How can we draw? So we know that is a triple bond. YNE means alkyne, triple bond. So C triple bond C, and the other fourth valency is satisfied by hydrogen. And C3H4 again C3. So 2 times 3 is 6. 6 minus 2 is 4 again. So this is alkyne. So 3 means prop is the prefix and YNE is the suffix. So we can draw C, one hydrogen here, 1, 2, 3 hydrogen on this carbon. So this is our Lewis dot structure, and the condensed structural formula will be CH3, C, and CH. Correct? Okay, and now how can we draw the skeletal formula? So here we have triple bond. That means here one carbon, and here another carbon, here another carbon. So for the triple bond, you have to be careful like that because it is sp hybridized. And now for the fourth one, it will be but, and we can see from the formula it is the suffix is going to be YNE because it's alkyne. And so there are 4 carbon atoms, 1, 2, 3, and 4, and I'm putting the triple bond 1, 2, 3, 4, 5, 6 hydrogen. How can I draw the, or how can I write the condensed structural formula? CH3, I have CH2 and one carbon here with a CH here. How am I going to draw? The skeletal formula is first carbon, second carbon, third carbon, and fourth carbon. So third carbon and fourth carbon here, triple bond. So one here, two here, third carbon here, and fourth carbon here. Two is here. Okay, so now this one is going to be C5H8. So that means pent is the prefix, and we can see from the formula that is an alkyne. So YNE is going to be the suffix. So 1, 2, 3, 4, and 5. So let me put the triple bond somewhere else so that you can see the difference. Let me put here. So here 1, 2, 3, and here 4, 5, 6, 7, 8. These two carbon atoms here, second and third carbon atom is already having 4 bonds around it. So what is going to be the condensed formula? I have CH3, I have carbon and another carbon, and CH2 and CH3. How can I draw? The structure skeletal formula is the first carbon is here, and that is bonded to a triple bonded carbon. That's the second carbon. And I have the third carbon and the fourth carbon. So this is going to be the third one. This is going to be the fourth one. I have the fifth carbon here. So where is the triple bond? Triple bond is in between second and third. So this is sp hybridized and this is sp hybridized. So it's going to be linear. So that's the reason we had to draw pentine like this. So just practice, and this is a good review from chapter 1. So far we have been discussing these groups. They are hydrocarbons. So we discussed this one, and we discussed aliphatic, what is the meaning of aromatic, single bonded, double bonded, and triple bonded. So also we have discussed this is saturated and very unreactive, and we said that these two are unsaturated, so they are reactive. Both are reactive. The reason for that one is the presence of double bond and triple bond. So that is the structural features of pi bonds, right? Both contain pi bonds. So the pi bonds are, the presence of pi bond makes it reactive. And now we are going to discuss the one with a heteroatom, that is Z, other than hydrogen, carbon bonded to another element other than hydrogen. So heteroatom. So we are done with this one too. So we are going to discuss this one and we are going to discuss this one now. Okay. So all these are functional groups except for the saturated one. Everything else we got functional group because they exhibit a wide range of properties, both physical and chemical properties. So the families are distinguished by group of atoms, or just like we have seen the structural features of pi bond. So they are called functional group. Okay, so they distinguish one organic molecule from the other, and they determine the geometry of the molecule as well, and reactivity. If you look at this molecule here, that is ethane. So two carbon atom bonded by single bond, single sigma bond here, and everywhere it is sigma bond. That means it is saturated. So it is very unreactive, right? That means there is no functional group here. At the same time, that's the same molecule here, which is represented by 3D model with a ball and stick model. So same explanation, all sigma bonds. Okay, so here you can see if one of the hydrogen is replaced by a hydroxy group here, oxygen and hydrogen, hydroxy group. What happens here is that is giving some properties which is entirely different from properties of ethane. So that is why we call that OH group as a functional group. That determines the properties of this compound, and the name is also different. If the OH group is attached, that hydroxy group is attached, we end the name with the OL instead of E. So the name is changed, the compound is changed, the property is changed, the geometry is also changed. So the hydroxy group makes the properties, which is very different from ethane. So ethanol has lone pair. So it makes that, because of that lone pair and the structure, it makes its polar compound. Whereas this is non-polar compound, another property, right? Okay, so other molecule with the hydroxy group will have the similar properties of ethanol. So whenever we have, this is only 2 carbon atom attached with the 1 hydroxyl group. If we have 3 or 4 or 5 carbon atoms or any other group here, and hydroxyl group is attached, all these groups will have similar properties. So in general, we can represent, irrespective of the number of carbon atom, we can just say this is any carbon skeleton by the letter R and a functional group. Here we just learned the functional group OH. So this can be a general formula for a functional group OH attached to a carbon skeleton. So in the ball and stick model, we will show that one with a different color here. You can see this. Okay, so then we can revisit this one later for more details in another chapter. So the Z can be any other atom other than hydrogen. So that makes it, if there is a lone pair and it is more electronegative, that makes it more polar. Okay, so the polarity is represented by the dipole moment with an arrow pointing towards a more electronegative atom and a small line in the beginning of the arrow. These electronegative atoms in the functional group make the molecule polar as well as more reactive. So the reactivity is due to the electronegativity. So oxygen is more electronegative than carbon, so the shared pair of electron will move towards oxygen, and that makes it slightly negative. Since it is slightly negative, we call it as a nucleophile because it is electron rich, and carbon is having a slightly positive charge. That makes it as electrophile because it is electron deficient. So that makes it more reactive. And in the case of pi bonds are electron rich, so we call it as nucleophile. So it will look for more positive sides to react with. So the pi bond is easily broken. So these are the reason for the high reactivity of functional groups. The common functional groups we will see in our organic chemistry is, other than the alcohol we just have seen, we will have more functional group like any halogen can be attached to that carbon chain. And then we will have halides, halo group. And alcohol we just explained. And ether means 2 carbon chain on both sides of oxygen. You can see that example. And that is called alkoxy group. If NH2 is attached, we call it as amino group. And if SH is attached, we call it as mercapto group. And if SR is attached, alkyl thio group. These are some of the functional group you will be seeing in organic chemistry. Here is an example of chloroethane used as local anesthetic that numbs the site of an injury. Several simple compounds like this are used in medicine, right? They are widely used. Just wanted to remind you, we can classify this one just like hydrogen and carbon we named primary, secondary, and tertiary. So these functional groups also can be classified as primary, secondary, and tertiary. So the functional group attached to the primary carbon will be primary. If it is OH group attached, we call it as primary alcohol. If it is halide, any chloride, bromide, iodide, any halide, we call it as primary alkyl halide. Same thing with the secondary alcohol and tertiary alcohol, tertiary alkyl halide, secondary alkyl halide. And the skeletal structure also given, you should be able to identify from the skeletal structure as well. And now the last category is the carbonyl, that is, it is attached to carbon, attached to double bonded to oxygen. Okay, so let us see that group. These are some examples of carbonyl groups. Say for example, aldehyde. The functional group is CHO, but the carbon is attached to that oxygen with a double bond, not like in alcohol. So in ketone also the same thing. Ketone is going to be on both sides the carbon chain, and in the middle it will be carbon to oxygen double bond. So you can see that structure, carbonyl group, so carbon attached to double bond. So this one is the skeletal form, and this one is acid. Acid is COOH. Okay, COOH will be the functional group. So when you write that one, it will be, when you draw the Lewis dot structure, you can see that it's going to be carbon double bond oxygen. So the functional group is COOH attached to the R. And this is going to be RCOR. This one is going to be RCHO. We will not be seeing always like this. We will not be seeing always like this. So you should be able to identify. So CHO, CO, either CO2H or COOH. But in all these cases, the idea is it is connected to the double bonded carbon, oxygen. Okay, carbon is double bonded to oxygen. So the names are different. So this is acid, ketone, aldehyde. The next one is going to be ester. If it is COO, CH3, COO, or just CO2, CH3. In that case, you should be able to identify that one as an ester. Most of the food, you can see that the aroma is coming from by adding ester. Okay, so you can see amide, so that is going to be CONH2, and acid chloride, COCl. In all these cases, carbon is double bonded to oxygen when you draw the Lewis dot structure. Again, when the functional group is attached to the primary carbon, we call it as primary amide. In this case, we took the example of amide. So if it is attached to a secondary carbon, it is secondary amide. If it is attached to tertiary carbon, it is going to be tertiary amide. The skeletal structure here, you can see the primary amide, it is connected to only one carbon, and the secondary amide attached to that nitrogen is attached to two other carbon, and in the tertiary amide you can see 1, 2, 3 carbons around it. So both way you should be able to identify primary, secondary, and tertiary. So to summarize, what's the importance of functional group? The functional group determines all of the following properties. So we have seen that bonding and shape, and the type and strength of intermolecular forces, that's what I'm going to explain next, and physical properties and nomenclature and chemical reactivity. So all these are there. So what we are going to do in this module is we are going to explain these two in detail, okay? And the other one we will explain in the respective chapters for each functional group, okay?